How many times have you trained an amazing computer vision model on a cloud GPU, hit fantastic accuracy metrics, but the moment you try to deploy that model into an edge device, the latency is an absolute disaster, the video feed stutters, the processor overheats, the project stalls. Most of us are taught that efficient architecture is a universal concept. We assume that if a model like MobileNet or YOLO works in theory, or has low flop count, it will be fast everywhere. The reality of Edge AI is much harsher. Today we are going to talk about why your AI architecture needs to shapeshift depending on where it's running, why GPU optimized models look completely different from CPU optimized ones. One of the most common mistakes people make in AI engineering is using flops, floating point operations per second, as the sole metric for speed. Flops don't tell the whole story. This is where techniques like hardware-aware NAS comes into play. Instead of designing a neural network by hand, we use algorithms like proxyless NAS to automatically test and find the best architecture. And when we let the algorithm search for the fastest network specifically for a GPU, and then specifically for a CPU, a fascinating pattern emerges. The hardware dictates the geometric shape of your network. Let's look at GPUs first. When NAS optimizes a model for graphic cards, it tends to build architectures that are shallower but wider. And why is that? Well, GPUs have massive parallel computing power, and thus multiplying a gigantic matrix is no problem for them. However, they have a very unique weakness, which is each kernel call is very expensive. Thus, the NAS algorithm tries to minimize kernel calls by widening the network layers. This makes the network depth smaller, but keeps the network expressiveness. But what happens when we optimize for a CPU, which is the heartbeat of so many edge AI devices out in the field? The architecture flips. Models optimized for CPUs tend to be deeper but narrower. Unlike GPUs, CPUs can handle function calls very cheaply and quickly, but they struggle heavily with massive matrix math. Therefore, the search optimizes for many small operations distributed across multiple layers, rather than a few colossal ones. In practice, building computer vision systems to run on the edge teaches you a very hard lesson. Many people think that you can just grab a GPU-trained and optimized model off the shelf, put in some quantization and pruning at the end of the pipeline, make it run efficiently on any device. Those techniques are essential, of course, but if your foundational architecture has the wrong shape for your device, for instance, if it's too wide for your ARM processor or NPU, pruning and quantization can only get you so far. After all, you're still leaving raw performance on the table. The key takeaway here is this: efficiency is not universal. A model that works pretty well on an NVIDIA GPU can be very bad to deploy on the edge. And that's not because of flops or parameter count, it's just the model structure. Therefore, the next time you are building a product to deploy on the edge, the first step is to keep your hardware target in mind before choosing the right architecture. This video helped you look at model optimization from a different angle. Leave a like and subscribe to the channel. We'll keep dissecting the real engineering challenges in Edge AI and computer vision here. I'll see you in the next one.